Good morning, ladies and gentlemen. Welcome to my presentation today on tailored materials and efficient processes for AM industrialization. My name is Philipp Imgrund. I'm the head of the AM processes department at Fraunhofer IAPT in Hamburg. I want to start my presentation with an introduction on Fraunhofer IAPT, Fraunhofer Research Institution for Additive Manufacturing Technologies. We were founded in 2018 as the 17th institute of the Fraunhofer Gesellschaft, which is the largest institution for applied research in Europe. We are located here in the southeast of Hamburg in Bergedorf, and we originated from the LZN, Laserzentrum Nord GmbH, and some parts of the Institute for Laser and Systems Technology of the Technical University of Hamburg. Currently, we're about 100 employees, and we're working in 3 departments, AM design, processes, and systems. And overall, the mission of the Institute is to provide industrial solutions for additive manufacturing technologies along the whole process chain, and also to integrate these process chains into industry and to provide safe, reliable, cost-efficient AM technology to our customers. So where did it all start? I want to give you a brief overview. The first adopters of metal AM were certainly aerospace, as you all know. In 2014, we got first press when we published the work together with Airbus on the FCRC bracket, the first titanium bracket for structural application. It's now flying in the Airbus A350. And this was really also for us as an institution a booster for being known and for starting off our activities and growing from a laser technology oriented institution into laser additive manufacturing. And also it was, I think, one of the first milestones for metal AM research in civil aircraft. It then went on with a European project, Bionic Aircraft, which I had the pleasure to coordinate. This project ran from 2016 to 2019, and it was dedicated to, I would say, converging the new materials for additive manufacturing aspect to bionic design principles and incorporating it into an application. And so what you can see here is we developed a couple of demonstrators in an aluminium silicon scandium alloy, originating from this mill design to a bionic optimized design in aluminium silicon scandium. We achieved a 28% weight reduction and also 30% reduction on potential with regards to carbon dioxide emissions. Of course, the whole project was dedicated to optimizing materials, looking at quality assurance systems, implementing design software, and so on. So if you're interested, feel free to look up the results of this project online. If you type in bionic aircraft, you will find all the information and a nice film also giving you some more insights into this project. And the second main user and adopter of AM nowadays is certainly automotive. Here back in 2016, we started a collaboration with ADAC, also in connection with Concept later, they're now a GE additive company, where we developed 3D printed nodes for the space frame and also developed a laser welding process for the space frame application. And it continued towards the production of this titanium brake caliper in connection with Bugatti. At that point, it was the world's largest 3D printed titanium part. And you can see in this video an insight in the production of this part. It was done on our SLM 500 in our facilities in Bergedorf. And the overall printing time on the 4-laser machine was about 45 hours. Due to the use of the titanium and to really designing the part from the beginning for additive manufacturing, providing space to eliminate the supports. We achieved a construction that was in the end 40% lighter than the original design. The part has now passed the brake tests and is being manufactured on demand. And so if you are a customer of the Bugatti Chiron, you would be able to also order this additive manufactured brake caliper. Of course, nowadays with the crisis, we all know that both automotive and aerospace are struggling a bit. We have a lot of projects in the medical field right now. Also on the polymer side, we're able to help with the COVID crisis in the field of polymer-based technologies, providing face shields and personal protective equipment from our SLS printers that you can see here. Of course, with regards to polymers, this is not our main focus. Our daily business is, of course, also here providing materials and optimizing process technologies for the polymer industry. So this is a field that is now growing apart from LBM. I want to stress that we have invested in sinter-based additive technologies, as it is also a polymer-based shaping process. We have arranged this in the polymer and sinter-based AM department. We have been working with a digital metal binder jetter for 2 weeks now. So very excited to provide this new addition to our portfolio, along with industrial polymer extrusion and also industrial metal fused filament fabrication, and also with a desktop metal studio system bound metal deposition, including the debinding and sintering technology. So really now the institution is developing from laser beam melting over polymer to sinter-based technologies, and also traditional field that is still evolving quite well is the field of directed energy deposition, where we're performing laser powder, laser wire processes. And we also have this big closed portal here where we are able to do large-scale 3D printing of metal, polymers, and also concrete. Yeah. So if you're interested in more detail in the technology portfolio, just feel free to contact me, and I will gladly discuss with you. So as you see, broad equipment, but for today I want to focus on laser beam melting and our means of increasing cost efficiency and productivity, and also tailoring materials to function. The basis of our work is represented by a study that we conducted back in the end of 2016, where we found that the cost potential, the main cost potential to reduce costs in AM for metals is within the process and the SLM machine itself, and within the SLM machine, exposure time and recoating time represents a major potential for cutting time and cutting cost. And so we looked at different possibilities to perform this. One means to reduce build-up time is, of course, increasing the layer thickness during the recoating. And in collaboration with an industrial partner, we have developed 90 micron parameters for aluminum silicon 10 magnesium for high performance, which means in this case maintaining high density and ductility in the part. We're in the range of 50 cubic centimeter per hour for aluminum silicon 10 magnesium here. And for the high speed parameter, based on a one laser solution, we're at 55 cubic centimeter per hour. Some investigations are still ongoing to increase this. So of course, increasing the layer thickness without sacrificing density and without creating defects in the structure is a means of increasing the productivity. A second means is reducing density on purpose. Also, some industrial partners of us and also competitors are working on this. We have found on a specific tool steel that while we achieve 10 cubic centimeter per hour build rate, again on a one laser machine for highest density, if we allow for 99.6% density instead of nearly 100, we can increase the build rate by a factor of 2.5. And by just doing this, we have a cost savings potential due to the increased build-up rate of 27% per part. In the first investigations, we didn't see any adverse effect on static mechanical properties. We find some correlations between the pore distribution and the size distribution and elongation. This is still under investigation, and there will be more results to come on this end. And a third aspect that we're putting a lot of effort in, we started this within the bionic aircraft project that I presented before, is the field of non-conventional beam shapes. We have installed a beam shaper on our Equinity Lab system here, which allows us to create such donut-shaped profiles or M-shaped profiles. And this in turn gives a more evenly distributed energy intake into the powder bed. And if you look at the videos here, you see that with a donut profile, you have considerably lower amount of spattering, much more smooth process to work with. Also, when using the donut profile, you see here for the laser power and the scan speed, in the process field, you have a much larger process field to come to high densities and to integral parts. For instance, here with higher laser power in the Gaussian field, you will have the balling effect and therefore no more secure production with regards to density. In the donut, you will have still a smooth and stable melt pool, allowing you to work in this range of speed. So it allows higher productivity and at the same time a more stable melt pool instead of the balling effect that we want to eliminate, of course. So as you see, some potential in the process to optimize performance and cost. And final aspect that I want to touch briefly on is process optimization by material performance. So what do we mean by that? For a given structure that you can see here, you have the possibility to print it in aluminium alloy or steel alloy. And of course, the specific strength of the steel alloy is a lot higher. So it allows you to build with less volume and still maintaining the strength prerequisites of the part. And even though, of course, scan speed for aluminium and specific weight of aluminium is a lot better compared to steel, it may still pay off to look at the alternatives because you can save material and you can still come up with higher productivity when producing such a steel part, giving you the same performance as the comparable aluminium part. So Of course, here we will also be glad to give some advice in the material selection and properly designing the process from the ground up. For a deeper look into the materials, we have a group which is very much dedicated to investigating the powders with regards to their characteristics and the influence of, for instance, the shape of the powder, also the condition of the powder, oxygen uptake during the process, humidity uptake, what does it do to the properties. And I want to give you the example also from the bionic aircraft project here, where we performed a material development for an aluminium silicon scandium alloy, leading to ultimate tensile strength of 553 megapascal in the as-built state, and in the heat-treated state 500 megapascal, 494. And the ductility in this case was around 5 to 6%, which is quite okay, I would say, for silicon scandium based material. And in the end, we came to these topology optimized demonstrators that I have shown you previously already. So when looking into automotive applications, we didn't want to optimize for strength, but for ductility. And we're very content to have a patent pending alloy Castalloy, which we developed in the customer 3D consortium. Here you see a comparison of a crash test for aluminum silicon 10, where you have a brittle crash and failure of the material, spatters flying around. And in the Castalloy, you see a really smooth bending of the structure in the crash test. And in the means of technology characteristics, we see that the elongation of the material is about 30% higher, increasing from 20 to 26%. But most important, the bending angle is increasing from 50 to 96.5 degrees, which makes for this really folding behavior of the alloy. Now we have transferred this material to our application demonstrator, which you can see here. It was built in 2 parts, and it was then laser welded together. And all together, together with the design of these parts, we were able to save up to 37% in weight, and it was also tested in the EDAC concept car. A next project example that I just want to touch briefly on is the development of aluminium nickel iron and aluminium silicon copper alloys, also for automotive applications. In this case, the specialty of this project was that we had a hybrid approach. So we combined a conventionally manufactured base part that we included into our SLM system. And we printed the functional structure here made of the PLM 905 onto the base structure. And the main process task was here to precisely position the laser so that you don't get inaccuracies in the print process when when joining the SLM part to the base plate. And we achieved this by implementing a no CT sensor, so optical coherence tomography sensor, into our LBM machine. So including such systems here is also an aspect and a specialty, I would say, of the department. And well, the part is now also being tested. The brake disc is being tested at our industry partner. Characteristics: 600 megapascal ultimate tensile strength, 520 megapascal yield strength, and of course very much directed to strength, 1% elongation. Finishing off my presentation with a short insight into our IAPT surface studies. Last year at this time, we presented on the Formnext show our surface benchmark study, where we compared the effect of different surface finishing methods, titanium, aluminium, and steel, on titanium, aluminium, and steel. And this year we conducted a study on titanium and Inconel with regards to the effect of surface finish on the mechanical properties with a focus on fatigue. And so this will be published shortly to our customers. And the surface benchmark study is already available, of course. It can be bought and purchased from us. I think it gives a high value insight on the influence of these finishing technologies here on surface roughness, penetration depth, edge rounding, and so on. So you will get a 120-page report dedicated to the influence of different surface finish on these three materials here. And here, just as a teaser, you can see the appearance of our demonstrators for titanium 6.4. I think in general, finishing is one aspect to consider from the very beginning of the process chain. The part isn't ready when printed, as you all know, and we are working towards integrating finishing procedures on the metal side and on the polymer side into our processes, providing you integrated AM solutions. And with this, I would like to finish my presentation. Thank you very much for listening. I'm available on the Formnext Connect. You can get in touch with me also via email and of course via LinkedIn as well. Thank you very much and have a good day.